444 million years ago, planet Earth was a graveyard. The end of the Ordovician period brought about the second largest mass extinction event in the history of our world. A sudden and severe ice age had locked massive volumes of the planetary water into continental glaciers across the southern hemisphere. Sea levels plummeted and marine ecosystems systematically collapsed. But planetary climates are not static, and this global deep freeze was merely a temporary state. As atmospheric dynamics shifted, global temperatures began a rapid, aggressive climb. The vast ice sheets fractured, collapsed, and melted. Unimaginable quantities of liquid water surged back into the global ocean basins. This was not simply a return to the previous baseline. The rapid influx of water caused global sea levels to rise to unprecedented heights, fundamentally altering the surface geometry of the planet. Ocean water spilled over the edges of the land masses, flooding the low-lying terrestrial basins. This specific geological mechanism created what we call Epicontinental seas, which are vast networks of shallow oceans resting directly on top of continental crust rather than oceanic crust. Because these waters were incredibly shallow, solar radiation could penetrate all the way to the submerged continental floor. This physical reality transformed the flooded continents into massive global solar incubators. The shallow water absorbed the thermal energy, creating a stable, warm environment that would become the perfect blank canvas for a new era of biological complexity. It was a world resetting itself, preparing to build an entirely new ecological architecture from the scattered survivors of a frozen apocalypse. Today, we are exploring the topic, the Silurian period, as we understand it. Before we dive into the deep time history of our planet and explore the mechanisms that shaped the modern world, please take a moment to like this video and subscribe to the channel. We also invite you to leave a comment down below, letting us know exactly where in the world and at what time you are watching this documentary. Now, let us step into the warming waters of the ancient Earth. To truly comprehend the biological revolution unfolding within these newly formed shallow seas, we must first examine the deep planetary engine driving the surface conditions. Earth in the early Silurian was physically unrecognizable from the map we know today. The southern hemisphere was overwhelmingly dominated by the massive supercontinent of Gondwana, a vast expanse of barren rock sitting largely over the South Pole. But the true geological violence and the ultimate catalyst for global change was occurring near the equator. Here, three distinct landmasses were on a slow, inexorable collision course. Laurentia, which contained the ancestral core of North America, Baltica, the precursor to modern northern Europe, and Avalonia, a microcontinent carrying the foundations of what would eventually become parts of Great Britain and the eastern seaboard of the United States. Between these landmasses lay the Iapetus Ocean. For millions of years, the oceanic crust of the Iapetus had been steadily sinking beneath the approaching continents through the process of subduction. Plate tectonics is often simplified as the movement of land, but fundamentally, it is a thermodynamic mechanism. It is the method by which a rocky planet expels its internal radioactive and primordial heat into the cold vacuum of space. The crust is merely the solidified skin of a convecting mantle. As the Iapetus ocean floor subducted and melted, it fueled volcanic island arcs, but eventually the ocean ran out of floor. The continents met. Because continental crust is primarily composed of lighter granitic rock, it is too buoyant to be forced down into the dense mantle. When continents collide, the incredible kinetic energy of the planetary heat engine has only one direction to go, and that is up. The collision of Laurentia, Baltica, and Avalonia triggered the Caledonian Orogeny, a monumental mountain-building event that permanently scarred the surface of the Earth. The resulting mountain range was staggering in its proportions, stretching across what is now eastern North America, through Greenland, Scotland, and deep into Scandinavia. Geologists estimate that at their peak, the Caledonian mountains rivaled or perhaps even exceeded the height of the modern Himalayas. But a mountain range of this magnitude is not just a static feature on a map. At a planetary scale, its meaning changes completely. Mountains of this size act as physical barricades in the atmosphere, abruptly altering the flow of global air currents. As moisture-laden winds coming off the global ocean hit the rising slopes of the Caledonian Range, the air was forced upward into cooler altitudes. This mechanism, known as orographic lift, causes the water vapor to condense and fall as massive amounts of precipitation on the windward side, while leaving the leeward side in a vast, arid rain shadow. The collision had essentially built a permanent, global weather modification machine. This leads to a deeper, far more significant consequence. The constant deluge of rain on the freshly uplifted granite initiated an aggressive process of chemical weathering. When atmospheric carbon dioxide dissolves in rainwater, it forms a weak carbonic acid. As this slightly acidic rain batters exposed silicate rock, it triggers a chemical reaction that strips the carbon out of the atmosphere, binding it with calcium and other minerals, which are then washed by river systems down into the oceans. This process, known as the silicate weathering thermostat, is the single most important climate stabilization mechanism on Earth. By pushing thousands of miles of fresh rock into the sky, the Caledonian orogeny drastically accelerated this weathering process. It pulled immense volumes of greenhouse gases out of the Silurian atmosphere, preventing the planet from entering a runaway greenhouse state as the sun continued to slowly increase its stellar luminosity. And right here, this mechanism begins to connect with a much larger question. When modern astrobiologists look at the night sky, searching for habitable exoplanets, they are deeply concerned with plate tectonics. A rocky planet without active plate tectonics, like Mars, has no way to recycle its carbon. Without mountain building to expose fresh rock, and without subduction to eventually melt and release carbon back through volcanoes, a planet's atmospheric cycle stalls. It either loses its atmosphere entirely, or it suffocates under an unbroken blanket of heat-trapping gas. Active geology is therefore a strict prerequisite for long-term biological survival. It is highly probable that the sheer rarity of sustained, perfectly balanced plate tectonics across billions of years acts as a great filter in the universe, a silent barrier that prevents countless promising worlds from ever sustaining complex life. Back on the Silurian Earth, the destruction of the mountains was just as important as their creation. The relentless weathering of the Caledonian peaks ground millions of tons of solid rock into microscopic sediment and dissolved mineral ions. Vast river systems, carving their way through barren landscapes utterly devoid of plant roots to hold the soil, carried an unprecedented influx of calcium, magnesium and silica directly into the warm, shallow epicontinental seas. This was not merely dirt washing into the ocean. It was an extraordinary delivery system for biological construction materials. The shallow seas were now saturated with the exact chemical compounds required to build hard structures. The geological violence of the continental collision had inadvertently loaded the oceans with the raw chemical fuel needed for the next great leap in complexity. The stage was perfectly set, chemically and thermally, for biology to begin building architecture on a scale the planet had never seen before. With the epicontinental seas saturated by the chemical runoff of the Caledonian mountains, the biological world was suddenly handed an infinite supply of building materials. The warm, shallow waters were now teeming with dissolved calcium and carbonate ions. Life, ever opportunistic, seized upon this chemical abundance and initiated one of the most profound biological revolutions in planetary history. This was the invention of massive biological architecture. Prior to the Silurian, marine life was largely restricted to dwelling directly on the flat ocean floor or floating passively in the water column. But now, organisms began to actively extract dissolved minerals to build rigid, permanent structures, introducing verticality to the oceanic landscape. The architects of this new world were not the scleractinian corals we see in modern oceans. The Silurian reefs were constructed by an entirely different consortium of organisms. The primary builders were the tabulate corals, which formed massive honeycomb-like colonies, and the rugose corals, often referred to as horn corals due to their solitary, cone-shaped structures. Working alongside them were the stromatoporoids, a now extinct group of sea sponges that secreted dense, layered mats of solid limestone. Together, they did not just inhabit the environment, they became the environment. They locked themselves into immense, interlocking frameworks that stretched for thousands of miles across the submerged continental shelves. But to truly understand these ancient structures, we must look beyond their physical shape and examine the molecular reality of their construction. At the quantum level, the crystallography of a Silurian reef is fundamentally alien compared to the Great Barrier Reef of today. Modern reef-building corals construct their skeletons using aragonite. Aragonite is a specific crystalline arrangement of calcium carbonate that is structurally dense but chemically relatively unstable over deep geological time. The tabulate and rugose corals of the Silurian, however, built their fortresses out of calcite. Calcite is a polymorph of calcium carbonate. It has the exact same chemical formula as aragonite, but its atoms are locked into a completely different geometric lattice. The calcite crystal structure is more hexagonal, less dense, and thermodynamically much more stable. This seemingly microscopic difference in atomic arrangement is the reason why Silurian reef fossils are so perfectly preserved today, while ancient aragonite reefs often dissolve or recrystallize into unrecognizable mounds of limestone. But this difference in crystallography was not a random evolutionary choice. It was forced upon biology by the internal thermal dynamics of the Earth itself. The ability of marine organisms to precipitate specific crystals is dictated by the ratio of magnesium to calcium in the ocean water. When the mid-ocean ridges are highly active, volcanically separating at rapid speeds to accommodate the shifting continents, huge volumes of seawater are drawn through the hot oceanic crust. This hydrothermal circulation strips magnesium out of the water and pumps calcium in. During the Silurian, the aggressive plate tectonics that formed the Caledonian mountains also drove rapid seafloor spreading. This created a profound drop in oceanic magnesium levels, resulting in what geologists call a calcite sea. In a calcite sea, it is physically difficult, thermodynamically unfavorable, and biologically expensive to secrete aragonite. The ocean chemistry actively suppresses it. Therefore, the early corals adapted to the planetary baseline, utilizing the naturally favored calcite to build their empires. This reveals a staggering reality about evolution. The microscopic building blocks of life are not completely autonomous. They are directly tethered to the tectonic heartbeat of the planet. The crystalline structures of biology are slaves to the geological machinery operating hundreds of miles beneath the Earth's crust. As these calcite structures grew upward toward the sunlight, they triggered a cascade of ecological consequences. A reef is fundamentally a manipulation of fluid dynamics. As ocean currents hit these massive three-dimensional frameworks, the water was forced to slow down, eddy, and swirl through the complex geometry of the coral branches and sponge mats. This mechanical disruption of the water flow caused microscopic organic debris and floating plankton to settle out of the current, effectively concentrating the food supply directly within the reef system. By altering the physical flow of the ocean, the reefs created highly specialized microclimates. They provided shaded crevices to hide from ultraviolet radiation, structural anchors to resist storm surges, and thousands of newly engineered ecological niches. For the first time, evolutionary pressure was applied, not just horizontally across the sea floor, but vertically. Species had to adapt to living inside, on top of, And underneath these biological skyscrapers, the reef became an engine of biodiversity, accelerating the arms race between predator and prey. And right here, this local biological phenomenon connects with the ultimate pursuit of modern astrobiology. When we search for evidence of life on other worlds, we are essentially looking for entities capable of altering their planetary environment in ways that abiotic chemistry cannot explain. The Silurian reefs represent one of the first times on Earth that biology achieved the scale of geology. These organisms extracted atmospheric carbon dioxide, processed it through the ocean, and locked it into gigatons of solid rock, permanently altering the carbon cycle of the planet. If we ever point our telescopes toward a distant exoplanet and detect vast, submerged platforms of concentrated calcium carbonate, we might not just be looking at a chemical anomaly. We might be witnessing the alien equivalent of a calcite sea. We would be observing a biosphere that has learned to geoengineer its own world, hijacking the planetary chemistry to build vast architectures. The emergence of the reef is a critical threshold. It is the moment life stops merely surviving on the surface of a rock and begins actively reconstructing the rock to serve its own survival. As the three-dimensional cities of calcite rose toward the surface of the epicontinental seas, the ocean floor below was heavily populated by a very specific and highly constrained class of early vertebrates. These were the Ostracoderms, the armored, jawless fishes of the Silurian. To look at them is to see an organism trapped in an extreme evolutionary defensive posture. Their bodies were encased in thick, overlapping plates of solid dermal bone, forming rigid head shields that looked more like geological formations than biological features. They were the dominant chordates of their time, but their physical design was essentially an evolutionary prison. This heavy dermal armor was not a lightweight biological choice. In the predatory arms race of the shallow seas, where massive arthropods ruled, heavy plating was the only viable survival strategy for a vertebrate that possessed no offensive weapons. The Ostracoderms had traded mobility, agility, and speed for the sheer blunt force of invulnerability. But this defense mechanism introduced a devastating biomechanical penalty. The water of the Silurian seas was dense and viscous, and fluid drag is a punishing force. The rigid, flattened head shields of the Ostracoderms acted like massive plows, creating huge, turbulent wakes that required immense muscular effort to push through the water. Furthermore, because most of these early jawless fishes lacked paired pectoral and pelvic fins, their pitch and yaw control was practically non-existent. They could not execute tight turns, rapid accelerations, or precise maneuvers. Their entire existence was a constant, exhausting battle against the gravity dragging their heavy bone plating downward and the fluid resistance pushing against their forward motion. But the true cost of this armor goes far deeper than fluid dynamics. It requires looking at the raw chemical economics of the body. Unlike the corals building the great reefs out of easily accessible calcium carbonate, the Ostracoderms constructed their armor using calcium phosphate. Phosphorus is an incredibly rare and biologically expensive element. It is the critical backbone of adenosine triphosphate, the universal molecular currency of cellular energy transfer in all living things. By locking vast reserves of precious phosphorus into dead external bone plating, these jawless fishes were hoarding a vital nutrient at the expense of their own internal metabolic potential. They were literally trading the chemical capacity for higher energy output for mechanical defense. This brings us to their most severe anatomical limitation. The Ostracoderms had no jaws. Their mouths were fixed gaping holes or simple muscular slits located on the underside of their armored heads. They survived by hovering just millimeters above the seabed, vacuuming up sediment and pushing the slurry out through their gill slits. The gills acted as a biological sieve, trapping microscopic organic detritus and absorbing dissolved oxygen simultaneously. This is the strategy of a bottom-feeding filter. It is slow, passive, and energetically incredibly poor. Here we encounter a fundamental boundary in biological engineering. Filter feeding on mud yields a remarkably low caloric return per unit of effort. When you combine a low-energy diet with a high-mass, heavily armored body, you hit a strict thermodynamic ceiling. An organism simply cannot grow larger or become more neurologically complex than its energy intake permits. The Ostracoderms were locked into a low-energy lifestyle. They were restricted to the mud, completely unable to exploit the rich, high-calorie prey swimming rapidly just above them in the water column. But the problem did not stop there. This design led to a deeper, almost fatal consequence regarding respiration. Because their gills were forced to perform two conflicting tasks at once, filtering thick mud for food and extracting dissolved oxygen for breathing, their metabolic rate was permanently throttled. If an ostracoderm needed to swim faster to escape a predator, its muscles required more oxygen. To get more oxygen, it had to pump more water through its gills. But pumping more water along the sea floor meant ingesting more mud, which physically clogged the very respiratory surfaces trying to absorb the oxygen. It was an inescapable anatomical catch-22. The hardware of their own bodies prevented them from ever scaling up their energy output. At a planetary scale, the implications of this physiological trap change completely. When modern astrobiologists consider the evolutionary pathways required to produce complex, intelligent, and eventually technological civilizations on exoplanets, they closely track the flow of energy. A biosphere dominated solely by passive filter feeders is a stagnant biosphere. To build large brains, to power complex social behaviors, and eventually to manipulate the physical environment, an organism requires highly concentrated, dense sources of calories. Predation is the universe's most efficient mechanism for energy concentration. One organism spends a lifetime slowly accumulating calories from microscopic plants, and a predator steals all of that accumulated solar energy in a single high-density meal. If a planetary ecosystem never evolves a biological mechanism for high-efficiency predation, its biosphere might simply plateau. It could remain a world of sluggish, armored filter feeders until the planet's star eventually expands and incinerates the world. The jawless condition of the Silurian vertebrates represents a localized evolutionary dead end, a biological great filter of its own. It demonstrates how easily life can survive for hundreds of millions of years without ever progressing toward higher complexity or intelligence. Life is perfectly content to be adequate. It does not inherently drive toward greatness unless forced by environmental pressure. For the vertebrates of the Silurian to break out of this thermodynamic prison, they needed a radical revolution in their skeletal architecture. They needed a way to separate the act of feeding from the act of breathing. They needed a mechanical tool to capture, kill, and process concentrated packets of energy. The passive vacuuming of the sea floor had reached its absolute physical and chemical limit. The ecological pressure to unlock the caloric wealth of the open oceans was mounting, and the solution would require violently repurposing the very internal structures that kept these ancient fishes breathing. To break the thermodynamic ceiling of the ocean floor, biology had to solve a mechanical engineering problem. The jawless vertebrates were trapped by the fundamental inefficiency of filter feeding, unable to access the highly concentrated calories swimming above them. But evolution is not an inventor, it is a tinkerer. It cannot summon entirely new anatomical structures out of nothing. It is forced to repurpose, modify, and heavily adapt whatever hardware is already present in the body. For the vertebrates of the early Silurian, the solution to their caloric deficit was hiding in the very apparatus they used to breathe. Behind the mouth of a jawless fish lay a series of cartilaginous rods known as gill arches. These structures acted as rigid V-shaped struts, holding the gill slits open so water could pass over the respiratory filaments. For millions of years, these arches served a singular, passive function. But as the oceans grew warmer and the competitive pressure of the shallow seas intensified, these fish required more oxygen to sustain sudden bursts of movement to escape giant predators. Here we encounter a critical shift in modern evolutionary theory. For decades, it was assumed that jaws evolved specifically for the purpose of biting prey. But modern biomechanical modeling suggests a very different sequence of events, known as the ventilation hypothesis. According to this model, the first pair of gill arches, the ones closest to the mouth, did not evolve to bite. They evolved to pump. By developing a flexible hinge in the center of the first gill arch and attaching stronger muscles to it, the fish could forcefully snap the arch shut. This action would violently squeeze the pharynx, driving a high-pressure wave of water backward over the gills. This innovation allowed the fish to actively ventilate their respiratory system while remaining completely stationary, immediately increasing their oxygen intake and raising their metabolic baseline. The ability to forcefully close an opening was originally a respiratory upgrade, an anatomical cheat code to extract more oxygen from the warm Silurian waters. But this mechanism leads to a deeper, far more significant consequence. Once a biological lineage possesses a muscular hinged structure at the front of its body, the exaptation of that structure is inevitable. A mechanism built to snap shut on water can just as easily snap shut on solid matter. Over millions of years, this first gill arch, now known as the mandibular arch, migrated forward. The second gill arch, the hyoid arch, shifted behind it to act as a structural brace, anchoring the new jaw securely to the braincase. This was the birth of the gnathostomes, the jawed vertebrates. Suddenly, the mouth was no longer a passive vacuum, it was a weapon. The earliest pioneers of this new architecture were the Acanthodians, small, spiny fish with rudimentary jaws, and the Placoderms, heavily armored vertebrates that quickly learned to weaponize their own dermal bone. Early placoderms did not possess true teeth. Instead, the edges of their jawbones extended outward and constantly rubbed against each other, creating self-sharpening, biological shearing blades, capable of slicing through the armored shells of their competitors. The invention of the jaw triggered a profound metabolic liberation. By separating the act of feeding from the act of breathing, vertebrates could finally harvest high-density packets of energy. A single bite of flesh provided more calories than hours of sifting through the mud. This sudden influx of thermodynamic wealth allowed the vertebrate body to fundamentally restructure itself. Because they no longer needed to hide under heavy external armor, jawed fishes could redirect their chemical resources. They began to internalize their skeletons, investing heavily in flexible cartilage, stronger muscles, and paired fins that provided true three-dimensional maneuverability in the water column. At a planetary scale, the meaning of this anatomical shift changes completely. The acquisition of the jaw is not merely a chapter in marine biology, it is the absolute prerequisite for the evolution of vertebrate intelligence. Neural tissue is the most calorically expensive material in the biological world. A complex brain requires a massive, continuous supply of energy. Furthermore, the act of active predation requires a creature to map three-dimensional space, calculate the trajectory of moving targets, and integrate visual, olfactory, and lateral line sensory data in real time. The brain was forced to expand simply to operate the new predatory machinery. Without the jaw to provide the necessary caloric density, the vertebrate brain would have forever remained a primitive knot of nerves. And right here, this biological mechanism begins to connect with a much larger question in astrobiology. When we look at the silent expanse of the universe and ponder the Fermi paradox, we must consider the specific, highly contingent bottlenecks of evolutionary history. The transition from a passive filter feeder to an active, high-energy predator might be a universal great filter. If life on an exoplanet fails to accidentally repurpose its anatomy to harness high-density energy, its biosphere will plateau. It will remain a world of simple, slow-moving organisms. The ability to bite is the biological spark that ignites the long, slow burn towards sentience, tool use, and eventually, technological civilization. However, there is a lingering shadow over our understanding of this monumental leap. The data provided by the fossil record is inherently biased. When we look at the rocks of the Silurian period, jawed fishes seem to appear abruptly, already highly diversified. Yet, modern geneticists utilizing molecular clocks, which calculate the rate of genetic mutation over time, argue that the common ancestor of all jawed vertebrates must have existed tens of millions of years earlier, deep in the Ordovician period. This discrepancy highlights the severe limits of our planetary observation. The earliest gnathostomes were likely small, fragile, cartilaginous creatures living in specific oceanic environments that were not conducive to fossil preservation. We are missing the crucial transitionary chapters of our own evolutionary history. What we see in the Silurian is not the invention of the jaw, but its explosive, highly successful deployment across the global oceans. But as these newly armed vertebrates began to test their power in the shallow seas, they quickly discovered that they were not the apex predators of this world. The waters were already ruled by an entirely different lineage of biological engineering, one that had mastered the art of aquatic warfare long before the first vertebrate ever learned to bite. While the early jawed fishes were busy internalizing their skeletons and experimenting with their new predatory hardware, they were stepping into an ecological arena that was already highly policed. The shallow epicontinental seas of the Silurian were ruled by a completely different paradigm of biological engineering. These were the Eurypterids, widely known as sea scorpions. They represented the absolute apex of arthropod evolution in the marine environment, and they had achieved a physical scale that makes their modern relatives look microscopic. Some species of Eurypterids grew to lengths exceeding 2 meters, making them the largest arthropods to ever exist on this planet. To understand how an insect-like creature could reach the size of a modern crocodile, we must examine the strict mechanical laws that govern biological architecture. Arthropods rely on an exoskeleton, a rigid outer shell composed primarily of chitin. This external armor provides excellent defense and highly efficient attachment points for internal muscles. However, from a biomechanical perspective, an exoskeleton is a fundamentally flawed design for achieving massive scale. The limitation is dictated by a geometric principle known as the square-cube law. As an organism grows larger, its proportions do not scale equally. If you double the length of an animal, its surface area, which determines the cross-sectional strength of its muscles and its exoskeleton, increases by a factor of 4. But its volume, which dictates its mass and the effect of gravity upon it, increases by a factor of 8. Because mass outpaces muscular strength so rapidly, a giant arthropod on land would quickly become a prisoner of its own weight. Its legs would shatter under the load of its heavy chitinous shell, and its internal organs would be crushed. But the physical rules of the universe operate differently depending on the medium. In the dense, viscous fluid of the Silurian oceans, the punishing effects of gravity were effectively neutralized by Archimedes' principle of buoyancy. Because the density of the sea scorpion's body was relatively close to the density of the salt water it inhabited, the upward buoyant force exerted by the displaced fluid counteracted the downward pull of gravity. Water acted as a universal gravity dampener, artificially supporting the massive weight of the chitinous armor. The ocean environment removed the mechanical ceiling imposed by the square-cube law, allowing the Eurypterid blueprint to expand to monstrous proportions. At a planetary scale, the meaning of this physical relationship changes completely. When astrobiologists model the potential fauna of exoplanets, gravity is a primary filtering mechanism. On a massive, rocky super-Earth, with twice the gravitational pull of our world, terrestrial life would be forced into low, squat, heavily reinforced configurations. Land-dwelling arthropods on such a planet would likely be restricted to millimeter scales. Yet within the oceans of that very same high-gravity world, the buoyant force of liquid water would still equalize the pressure. Aquatic alien environments offer a thermodynamic and mechanical sanctuary where massive biological architectures can thrive regardless of the planet's overall mass. Water is the great equalizer of the cosmos. Freed from the constraints of gravity, the giant sea scorpions optimized their hydrodynamics. Their bodies were heavily segmented, allowing for lateral flexibility, while their final pair of appendages evolved into wide, flattened paddles. These were not simply oars used to push water backward. Biomechanical simulations indicate that Eurypterids used these paddles in a complex, figure-8 sweeping motion, generating both thrust and hydrodynamic lift simultaneously. This is the exact same subaqueous flight mechanism utilized by modern sea turtles and penguins. It allowed these massive predators to hover silently in the water column or execute sudden, explosive bursts of speed to ambush the slower, heavily armored jawless fishes navigating the reefs. Furthermore, their primary weapons, the chelicerae, were highly specialized mechanical tools. Depending on the species, these front appendages were adapted either as massive, spiky, grasping claws to capture slippery prey, or as powerful, nutcracker-like crushers designed to shatter the calcium phosphate dermal bone of the early vertebrates. They were the ultimate biological machines, perfectly calibrated to dominate the Silurian waters. But this formidable design contained a fatal flaw, a biological vulnerability inherent to all arthropods. Because their skeleton was located on the outside of their bodies, and because chitin is dead, rigid tissue that cannot expand, a sea scorpion could not grow continuously. To increase its size, it was forced to undergo ecdysis, the process of molting. The animal had to literally split its old armor open, crawl out of its own skeleton, and rapidly absorb water to expand its new, highly flexible shell before it chemically hardened. This process created a profound ecological bottleneck. For several days during the molting cycle, the apex predator of the Silurian Sea was reduced to a soft, completely defenseless mass of protein. In a marine ecosystem that was rapidly filling with aggressive, newly evolved jawed fishes looking for high-density calories, molting in the open water was a death sentence. This vulnerability drove a radical shift in their behavior, leaving behind physical evidence that we can still read today. Fossilized trackways discovered in ancient tidal flats reveal that some species of Eurypterids began migrating out of the deeper waters. They used their paddles and walking legs to drag their heavy bodies into the extreme shallows, coastal lagoons, and sometimes, very briefly, straight out of the water and onto the exposed mud of the shoreline. They were seeking environments so shallow and so hostile that the jawed fishes could not follow them, creating safe havens to undergo their dangerous molting process or to mate. This leads to a deeper, far more significant consequence. By temporarily pushing themselves out of the buoyant safety of the water, these giant arthropods were unwittingly subjecting themselves to the full, crushing force of gravity, the searing heat of the sun, and the devastating lack of surrounding moisture. They were standing on the threshold of an entirely alien world. The land masses of the early Silurian were barren, irradiated, and utterly hostile to marine biology, but the very armor that made them so heavy and limited their growth in the physical domain was about to serve a completely different, life-saving chemical purpose in the atmospheric domain. When the giant sea scorpions briefly dragged their heavy armor out of the water, they were merely temporary visitors to an alien world. To truly conquer the continents, biology had to solve a lethal atmospheric equation. The terrestrial environment of the early Silurian was not a lush, green paradise. It was a sterile, unforgiving hellscape. Without a canopy of vegetation to absorb solar radiation, or a thick layer of topsoil to regulate thermal energy, the bare rock and silica sand baked under intense ultraviolet bombardment. Temperatures swung violently between searing daytime heat and freezing nights. The air was incredibly dry. For marine organisms entirely composed of water, stepping onto this barren rock was the biological equivalent of walking out of an airlock without a spacesuit. The ultimate barrier to leaving the ocean was not gravity. It was the fundamental physics of respiration. In the marine environment, animals breathe using gills. A gill is a marvel of fluid dynamics, consisting of thousands of microscopic, highly vascularized filaments designed to maximize surface area and extract dissolved oxygen from the water column. But this intricate biological architecture relies entirely on the physical properties of the liquid it operates in. Water provides the necessary buoyancy to keep the delicate filaments separated and suspended. The moment a marine creature is exposed to the atmosphere, this system suffers a catastrophic mechanical failure. Without the structural support of water, gravity forces the wet filaments to collapse and mat tightly together, instantly reducing the surface area available for gas exchange to near zero. Furthermore, the laws of biology dictate that oxygen can only diffuse across a cell membrane if that membrane is coated in a thin layer of moisture. In the dry Silurian air, exposed gills rapidly desiccate. The animal does not die because there is a lack of oxygen in the atmosphere. It suffocates because its biological hardware physically jams in a gaseous medium. To permanently colonize the landmasses, life required a radical redesign of its respiratory machinery. The fossil record points us to a microscopic pioneer discovered in the sedimentary rocks of Scotland, an ancient arthropod resembling a modern millipede named Pneumodesmus pneumani. For years, paleobiologists have fiercely debated its exact position in deep time, with some models placing it in the late Silurian, making it the oldest known air-breathing animal on Earth. Regardless of the precise geochronological dating, the anatomical evidence preserved in its fossilized segments represents a structural breakthrough that altered the trajectory of planetary evolution. Along the lateral segments of its body, this early myriapod had evolved a series of microscopic pores known as spiracles. These openings were not passive holes in the shell. They were highly engineered valves that served as the gateways to an extensive, branching network of internal tubes called the tracheal system. Instead of forcing the external environment over a specialized organ like a gill, the tracheal system piped gaseous oxygen directly into the deep interior of the animal, delivering it straight to the individual cellular tissues. This internal routing bypassed the need for a centralized lung or a heavy pressurized circulatory system to pump oxygenated blood. But the true physiological genius of the tracheal system lies in the raw physics of diffusion. Oxygen molecules diffuse roughly 10,000 times faster in a gaseous state than they do when dissolved in water. By transitioning to breathing atmospheric gas, these pioneer terrestrial arthropods unlocked an immediate, massive metabolic upgrade. Their cellular engines could run at a much higher capacity, allowing for sustained activity and rapid movement without the constant threat of oxygen debt. At a planetary scale, the meaning of this physiological shift changes completely. When modern astrobiologists model the probability of intelligent, technological civilizations emerging on exoplanets, they encounter a severe developmental ceiling on ocean worlds. A planet completely covered by a global sea might harbor incredibly diverse and complex marine ecosystems. However, liquid water is a terrible medium for high-energy chemistry. You cannot forge metallurgy underwater. You cannot discover the principles of electricity, harness the power of combustion, or build radio telescopes in a purely aquatic environment. An ocean world is permanently locked out of the industrial age by the basic laws of physics. Therefore, the biological transition from water to land and the specific evolutionary engineering required to breathe gas is not just a localized chapter in Earth's paleontology. It is a mandatory cosmic threshold. The invention of spiracles and internal gas diffusion was the absolute prerequisite for high metabolism terrestrial life. Without this anatomical leap, the continents of our world would have remained silent expanses of barren stone, and the very concept of a fire-wielding, technological civilization would be physically impossible. The leap to land is the ultimate great filter, separating complex biology from technological capability. But extracting oxygen from the harsh Silurian air solved only half of the survival equation. The tracheal system successfully brought life-giving gas deep into the body, but it simultaneously created a direct, open conduit to the dry atmosphere outside. In the brutal, arid environment of the primordial landmass, every breath was an exchange that cost the organism its most precious internal resource, which was water. If these early terrestrial pioneers could not find a physiological method to seal their bodies against the relentless desiccation of the air, their great invasion of the continents would end in rapid mummification. The internal tracheal system solved the physical mechanics of breathing atmospheric oxygen, but it immediately exposed these pioneer arthropods to a far more insidious threat. The atmosphere of the early Silurian was essentially a massive planetary sponge. To understand the lethality of this environment, we must look at the strict thermodynamic laws governing vapor pressure deficit. In a dry atmosphere, water molecules are subjected to an overwhelming physical mandate to diffuse from areas of high concentration to areas of low concentration. Because the internal tissues of a living organism are saturated with water, the dry air outside exerts a relentless pulling force on every microscopic drop of moisture within the biological system. If a marine organism steps onto land without adequate protection, the atmosphere will simply boil the water out of its cells through pure osmotic pressure, leading to rapid and catastrophic mummification. The thick, heavy chitinous armor that protected the giant sea scorpions in the ocean was entirely useless against this atmospheric theft. Chitin is an excellent structural material, capable of deflecting the crushing bite of a jawed fish. But in its basic form, it is highly permeable to water vapor. The early marine arthropods were effectively leaking their own life force into the dry air. To survive the terrestrial environment, biology did not need to build thicker armor. It needed to engineer an entirely new class of chemical defense. The solution was the evolution of the epicuticle, a microscopic outer boundary layered directly on top of the chitinous exoskeleton. This layer was completely invisible to the naked eye, yet it represented one of the most critical biochemical breakthroughs in the history of life. The epicuticle is not made of structural proteins or heavy minerals. It is composed of highly complex mixtures of long-chain hydrocarbons, lipids, and specialized waxes. From a biochemical perspective, waxes and lipids are profoundly hydrophobic. Their molecular structures lack the polarized electrical charges necessary to bond with water molecules. When a layer of wax is secreted over a surface, it creates an absolute chemical barricade. Water inside the organism is physically repelled by the inner surface of the lipid layer, trapping the moisture within the body cavity. By enveloping themselves in this microscopic sheen of hydrocarbon wax, these ancient terrestrial arthropods effectively severed the thermodynamic link between their internal fluids and the dry atmosphere. They became completely waterproof. This leads to a deeper, far more significant consequence regarding our understanding of terrestrial biology. When we look at animals walking on land, we often assume they have left the aquatic environment behind. But in reality, life never truly left the ocean. It simply learned how to encapsulate the ocean and carry it onto the dry rock. Every terrestrial organism on Earth today, including human beings, is essentially a walking, highly pressurized sack of ancient seawater, maintained entirely by complex, microscopic layers of hydrophobic lipids. The colonization of land was not an escape from water, but the biological mastery of its containment. At a planetary scale, the significance of this chemical barrier changes completely. When modern astrobiologists evaluate the potential for complex life on rocky exoplanets, they must account for the chemical inventory of the alien world. If an exoplanet harbors liquid water oceans, but lacks the specific precursor elements or the thermal conditions required to synthesize complex, hydrophobic molecules like long-chain hydrocarbons, its biosphere might be permanently trapped. Life could flourish in the alien seas for billions of years, but without the ability to chemically manufacture a waterproof seal, the dry continents will forever remain an impenetrable death zone. The ability to synthesize waxy lipids acts as a profound biological great filter. It is a mandatory chemical gate that every planetary biosphere must unlock before it can attempt to colonize the dry surface and eventually build a terrestrial civilization. But on the Silurian Earth, the invention of the epicuticle created a sudden physiological paradox. The arthropod had successfully sealed its entire body in waterproof wax, preventing lethal dehydration. However, it still needed to breathe. The microscopic breathing holes, the spiracles that connected the internal tracheal tubes to the outside air, were essentially punctures in the perfect waterproof armor. Every time the organism inhaled oxygen, the dry air swept into the respiratory tubes and stole internal moisture. To survive, the evolutionary arms race had to shift to micromechanical engineering. The spiracles could not remain permanently open. Over countless generations, the margins of these respiratory pores evolved highly sensitive muscular valves. These biological gates were tied directly to the nervous system, allowing the animal to continuously monitor the humidity and temperature of the outside air. During the searing heat of the Silurian day, when the vapor pressure deficit was at its most lethal, the muscular valves would snap shut, sealing the organism completely within its waxy vault. Only during the cooler, more humid nights or in shaded crevices would the valves flutter open to exchange carbon dioxide for fresh oxygen. This intricate dance between retaining water and acquiring oxygen allowed the first arthropods to push further away from the safety of the coastal mudflats. Armed with internal lungs and wrapped in chemical armor, they began to slowly march into the deep, hostile interiors of the supercontinents. They were carrying the first concentrated packets of organic carbon, nitrogen, and metabolic heat into regions of the planet that have been sterile since the formation of the Earth. However, this heroic invasion was ecologically unsustainable on its own. Animals are heterotrophs. They cannot produce their own energy. They are engines of consumption. An ecosystem composed entirely of wandering predators and scavengers will quickly exhaust its caloric reserves and collapse. To truly conquer the barren rock and build a permanent terrestrial biosphere, the animal kingdom desperately needed the plant kingdom to follow them out of the water. But for a plant to survive in the dry air, and more importantly, to stand upright against the crushing force of gravity without the buoyant support of water, the botanical world would have to invent an entirely new system of internal biological plumbing. For the newly waterproofed arthropods to establish a permanent, thriving ecosystem on the barren continents, they could not rely on scavenging the dead remains of marine life washing up on the shores. A true terrestrial biosphere requires a primary producer, an organism capable of harnessing solar energy and converting it into biological mass directly on the dry rock. The plant kingdom had to follow the animals out of the water, but as these ancient moss-like pioneers attempted to spread across the Silurian landscape, they slammed into a fundamental physical barrier. That barrier was the relentless downward force of planetary gravity. The earliest terrestrial plants were restricted to a two-dimensional existence. They hugged the wet margins of coastal lagoons, rarely growing more than a few millimeters tall. This extreme limitation was dictated by their reliance on simple cellular diffusion. In these primitive organisms, water moved passively from one cell to the next through osmosis. While osmosis is a perfectly efficient transport mechanism across microscopic distances, it is mathematically incapable of lifting a column of liquid against the gravitational pull of the Earth. If a non-vascular plant attempts to grow upward, The cells at its apex quickly dry out and die because the water simply cannot climb fast enough to replace what is lost to evaporation. To conquer the third dimension, biology had to invent a pipeline. The fossil record points us to a remarkably unassuming pioneer named Cooksonia. Found in the sedimentary rocks of the Middle Silurian, Cooksonia lacked leaves, it lacked true roots, and it was barely a few centimeters tall. Yet, cross-sections of its fossilized stems reveal a structural revolution that would permanently alter the surface of our world. Running through the center of its tiny stems were microscopic, elongated tubes. This was the dawn of vascular tissue, specifically the xylem. The evolution of the xylem represents a profound shift in biological engineering. The xylem is essentially a microscopic water pipe, but its design is deeply counterintuitive. The cells that make up the xylem must die in order to function. As they mature, these cells commit a highly programmed form of cellular suicide. They dissolve their own internal organs, clear out their cytoplasm, and break down their end walls, leaving behind only their rigid, hollow outer shells. Stacked end to end, these dead cell walls create a continuous, empty, microscopic straw, stretching from the damp soil up into the atmosphere. But a pipe is completely useless without a pump to drive the fluid through it. Animals evolved a muscular heart to pressurize their circulatory systems, but plants took a completely different thermodynamic approach. They outsourced the mechanical labor to the local star. When solar radiation strikes the top of a plant, it heats the tissues and causes water to evaporate into the dry air. Because water molecules are highly polar, they form strong hydrogen bonds with one another, effectively sticking together like a continuous molecular chain. When one water molecule evaporates and leaves the top of the xylem, the resulting microscopic vacuum pulls the next molecule up to take its place. This tension is transmitted down the entire length of the water column, all the way to the base of the plant. This mechanism is known as the cohesion tension theory, and it is a marvel of passive hydraulic engineering. The plant does not spend a single molecule of its own cellular energy to pump the water. The sun provides the evaporative engine, and the chemical properties of water provide the structural tensile strength. The early vascular plants had effectively weaponized solar radiation to defeat planetary gravity. At a planetary scale, the implications of this mechanism change completely. A terrestrial forest is not just a biological community, it is a massive, silent, solar-powered hydraulic machine. When modern astrobiologists model the potential for complex, towering plant life on exoplanets, they must carefully balance stellar luminosity against planetary mass. On a rocky super-Earth with high surface gravity, the weight of the internal water column would be immense. The gravitational pull would eventually overpower the hydrogen bonds holding the water molecules together, causing the fluid chain to snap. This physical failure, known as cavitation, creates a lethal air bubble that permanently blocks the vascular tube. Therefore, the maximum height of a biological forest is strictly governed by the mass of the planet it grows on. Towering canopies might be an incredibly rare phenomenon, restricted to worlds with a very specific, permissive gravitational threshold. Pumping water upward, however, only solved half of the circulatory problem. Once the top of the plant utilizes that water, along with atmospheric carbon dioxide and sunlight, to synthesize energy-rich sugars, that heavy, viscous biological fuel must be distributed back down to nourish the rest of the organism. This required the evolution of a second, parallel plumbing network, known as the phloem. Unlike the dead, hollow pipes of the xylem, the phloem is composed of living cells. Because sugar sap is too heavy to move efficiently through passive diffusion, the phloem relies on active chemical transport, using specialized companion cells to physically pressurize the vascular network and push the nutrients to wherever they are needed. The invention of this dual circulatory system severed the botanical world's absolute dependence on the moist boundary layer of the soil. It ignited a slow, silent, vertical arms race. In the competitive arena of biology, height is power. A plant that grows just a few centimeters taller than its neighbor can monopolize the incoming photons, casting a lethal shadow over its competition. The imperative to grow upward became the driving force of terrestrial evolution. But fluid dynamics alone cannot conquer the sky. As these early vascular plants attempted to stretch higher into the Silurian atmosphere, the physical forces acting upon them became extreme. The negative pressure created by the evaporative pull inside the xylem tubes was immense. Without heavy structural reinforcement, the vacuum inside the dead cells would simply cause the microscopic pipes to crush inward and collapse under the atmospheric pressure. To build a true vertical empire, the plant kingdom needed more than just plumbing. It needed to synthesize an entirely new class of biological armor, a molecular compound so rigid and so chemically indestructible that it would eventually overwhelm the digestive capabilities of the entire planet. To prevent the internal vacuum from crushing their newly evolved plumbing, the early plants had to become chemical engineers. The pressure differential generated by the evaporation of water was simply too great for standard cellular walls to withstand. Cellulose, the primary building block of plant matter, is a phenomenal material when subjected to tension. If you pull it, it holds with incredible strength, but it is fundamentally weak in compression. If you squeeze it or subject it to a powerful internal vacuum, it buckles and collapses. The botanical world required a completely different type of molecular reinforcement to armor its vascular network. The biological answer was the synthesis of a molecule called lignin. Unlike cellulose, which is a neat, highly ordered chain of identical sugar molecules, lignin is a chaotic three-dimensional polymer. Its molecular architecture is formed through a highly complex randomized polymerization process that creates a dense, heavily cross-linked chemical web. When a plant cell secretes lignin into the spaces of its cell wall, it acts exactly like the epoxy resin used in modern carbon fiber manufacturing. It binds the loose, flexible cellulose fibers together, locking them into a rigid, waterproof and mechanically indestructible matrix. Armed with lignified vascular tissue, plants could finally hold their water pipes open against the immense negative pressure of transpiration. Furthermore, they could now build vertical columns capable of supporting their own weight against the pull of gravity, allowing them to finally break free from the two-dimensional surface of the rock. But the invention of this biological concrete introduced a profound ecological paradox, one that would fundamentally alter the geology of the entire planet. Because the molecular structure of lignin is so complex and highly randomized, it is incredibly difficult to dismantle. Biological decomposition is driven by digestive enzymes, which function as highly specific molecular keys designed to unlock predictable molecular locks. Lignin was a lock with a randomized combination. The bacteria and fungi that existed in the Silurian period simply lacked the biochemical tools to break these complex carbon bonds apart. This created a severe disruption in the planetary carbon cycle. When these early lignified plants died, they did not rot. They simply fell over and remained largely intact. As millions of years passed, this indigestible organic matter began to pile up, permanently trapping vast quantities of atmospheric carbon on the surface of the continents. Simultaneously, the living plants were engaged in another aggressive process of terrestrial modification. While their stems reached upward into the atmosphere, their basal structures, known as rhizoids, anchored themselves directly to the bare rock. To survive, these plants needed to extract vital trace minerals like phosphorus, potassium, and magnesium from the planetary crust. To access these trapped nutrients, the rhizoids secreted powerful organic acids. This process, known as biological weathering, actively dissolved the underlying silicate rock, slowly crumbling the solid continental crust into microscopic mineral flakes. The mechanical mixing of this pulverized, chemically weathered rock with the accumulating layers of undecayed, lignified plant tissue created something entirely new in the history of the Earth. It created the first true topsoil. This leads to a far deeper consequence regarding planetary thermodynamics. Soil is fundamentally different from lifeless sand or crushed rock. It is a highly structured, dynamic biomaterial. At a microscopic level, the organic compounds within the soil carry slight electrical charges that bind tightly with water molecules. This transformed the terrestrial surface from a hard, reflective mirror into a massive, global hydrological sponge. Before the invention of soil, rainwater falling on the continents simply flashed off the bare rock in devastating immediate floods. But the new soil layer captured the precipitation, stored it, and slowly released it over time. This stabilized the global water cycle, creating permanent year-round river systems and buffering the terrestrial environment against sudden droughts. At a planetary scale, the meaning of this biological synthesis changes completely. When modern astrobiologists look to the stars and model the requirements for advanced technological civilizations, they are inherently searching for worlds with soil. A purely rocky exoplanet, even one possessing a breathable oxygen atmosphere and liquid water oceans, cannot support the dense, stationary population centers required to build an industrial base. Technological civilizations are entirely reliant upon the massive caloric surpluses generated by agriculture, and agriculture is strictly bound to the thermodynamic and chemical properties of topsoil. If the plant life on an alien world never stumbles upon a chemical polymer tough enough to resist immediate microbial decay, that planet will never accumulate an organic soil layer. The dead matter will simply decompose instantly, returning its carbon to the atmosphere. The planet's biosphere will remain a thin, fragile film, clinging to the rock, constantly vulnerable to hydrological extremes, and it will forever lack the agricultural battery necessary to power a technological species. The dirt beneath our feet is not a geological given. It is a highly engineered biological product, and its creation serves as a critical great filter in the cosmos. However, while these early vascular plants were slowly dissolving the rocks and laying down the first millimeter-thick layers of primitive soil, the Silurian landscape was not entirely composed of microscopic flora. As the first arthropods crawled through this newly forming terrestrial ecosystem, they found themselves moving through the shadows of something truly baffling. Rising from the primitive dirt were biological structures of such massive proportions and alien design that for over a century, modern science fundamentally misunderstood what they were. As the earliest vascular plants struggled to raise their stems a few centimeters above the mud, they were entirely dwarfed by the true masters of the Silurian continents. Towering over the primitive mossy landscape were monolithic pillar-like structures that reached staggering heights of up to 8 meters, with trunks measuring a full meter in diameter. For over a century, these enigmatic fossils, named Prototaxites, represented one of the most frustrating biological paradoxes in the history of paleontology. The paradox lies in the sheer physics of their existence. Based on the mechanical laws of biology, Prototaxites simply should not have been there. Building a towering biological structure requires a highly engineered internal plumbing system, reinforced by complex polymers to fight gravity and atmospheric vacuum pressure. Yet, when paleobotanists sliced these giant pillars open and placed them under microscopes, they found absolutely no evidence of xylem, phloem, or woody tissue. Instead, the internal architecture consisted entirely of tightly woven, microscopic tubes lacking any structural reinforcement. Without the traditional anatomical markers of a tree, the scientific community fractured into competing hypotheses. Was Prototaxites a primitive conifer that somehow decayed strangely during fossilization? Was it a colossal marine algae that washed ashore and rolled up into giant mats? Or was it an unprecedented form of terrestrial lichen? Relying purely on physical morphology, the shape and structure of the fossil, scientists had hit a permanent analytical wall. To To solve the mystery of the Silurian monoliths, modern science had to abandon physical anatomy and descend into the quantum realm of the atom. The answer was locked inside the carbon isotopes preserved within the ancient tissues. Carbon exists in two stable forms in the atmosphere: the lighter, highly abundant carbon-12 and the heavier, much rarer carbon-13. When an autotrophic organism, like a green plant, photosynthesizes, its cellular machinery exhibits a strict physical bias. The primary enzyme responsible for capturing carbon dioxide specifically prefers the lighter carbon-12 molecule because it requires less thermodynamic energy to process. Therefore, every photosynthetic plant on Earth, regardless of where it grows, exhibits a relatively predictable, uniform ratio of carbon-12 to carbon-13 in its tissues. This is the unmistakable chemical fingerprint of photosynthesis. But heterotrophs, organisms that cannot make their own food and must consume other organic matter, operate under completely different chemical rules. A heterotroph simply absorbs the isotopic signature of whatever it eats. When geochemists analyzed samples of Prototaxites gathered from different fossil sites around the world, the data was shocking. The isotopic ratios were wildly erratic. Some specimens were rich in carbon-13, while others from different locations were highly depleted. This erratic chemical signature proved beyond a shadow of a doubt that Prototaxites was not photosynthesizing. It was not a plant. It was a colossal, heterotrophic organism consuming a highly variable, localized food supply. The towering monoliths of the Silurian were giant fungi. To construct an 8-meter-tall fruiting body, a fungus requires a staggering caloric intake. The visible pillar was merely the reproductive spire of a vastly larger, invisible organism. Beneath the primitive Silurian soil, Prototaxites operated an extensive, subterranean mycelial network stretching across acres of land. These microscopic fungal threads acted as the ultimate chemical scavengers. They secreted powerful enzymes to break down the dead, indigestible biological crust of early plants and cyanobacteria, slowly absorbing the trapped carbon and using osmotic pressure to pump it upward, slowly constructing their massive spires over decades. At a planetary scale, the meaning of this bizarre biological reality changes completely. When we imagine alien biospheres on distant exoplanets, we inherently project the biological hierarchy of modern Earth, assuming that plant-like producers will always dominate the physical landscape, while consumers remain relatively small or mobile. Prototaxites completely shatters that assumption. It proves that a terrestrial ecosystem can be entirely dominated by giant, stationary heterotrophs, while the photosynthetic producers remain microscopic. An alien world could theoretically sustain a towering, planet-wide forest constructed entirely of giant fungal equivalents, feeding on a microscopic carpet of algae. Life does not have to look like Earth to function efficiently, and our search for extraterrestrial life must account for these inverted ecological plateaus. However, the reign of the giant fungi was intrinsically tied to a very specific, fragile ecological window. As we move forward in deep time, Prototaxites abruptly vanishes from the fossil record. This extinction was not caused by a sudden asteroid impact or a catastrophic volcanic winter. It was driven by the ruthless, grinding efficiency of biological competition and planetary evolution. As the small vascular plants eventually mastered the synthesis of woody tissue, they began to grow taller, branching out to capture the sunlight and drastically altering the surface microclimates. The plants were no longer just a food source on the ground, they became a physical barrier in the sky. Simultaneously, the first terrestrial arthropods were rapidly evolving. Freed from the oceans and armed with complex internal respiratory systems, these early insects began developing specialized jaw structures capable of chewing and digesting tough fungal tissue. Prototaxites, a slow-growing, highly nutritious tower of stationary calories, suddenly found itself outcompeted for physical space by the first true trees and heavily predated upon by the first terrestrial herbivores. It had no defensive mechanisms, no poison, and no bark. The giant fungi was simply consumed from the bottom up and overshadowed from the top down. The towering monoliths collapsed, marking the end of the fungal empires and permanently transferring the dominion of the continents over to the kingdom of plants. This shift fundamentally locked the planetary biosphere into the modern, plant-dominated hierarchy we recognize today, setting the stage for the massive forests that would eventually alter the global climate and drive the Silurian period toward its mysterious and suffocating conclusion. As the towering fungal monoliths collapsed and the first true vascular plants began to aggressively alter the chemistry of the continents, the Silurian period did not glide peacefully into a stable future. The late Silurian was an era defined by violent planetary-scale instability. To understand the sheer magnitude of these environmental crashes, we cannot rely solely on the physical shapes of fossils. An empty shell can tell us what an animal looked like, but it cannot tell us the temperature of the water it swam in or the chemical composition of the air it breathed. To reconstruct the invisible climate of a vanished world, modern science must abandon paleontology and descend into the atomic memory of the planet. The most powerful tool we possess for decoding deep-time climate is the ratio of oxygen isotopes preserved in ancient marine limestone. In the global water cycle, oxygen exists primarily in two stable forms: the lighter, highly abundant oxygen-16 and the heavier, much rarer oxygen-18. This microscopic difference in atomic mass dictates how these isotopes interact with thermodynamic energy. Because oxygen-16 is lighter, it requires less kinetic energy to break its liquid bonds and evaporate into the atmosphere. During a global ice age, this lighter oxygen-16 evaporates from the oceans, falls as snow over the continents, and becomes permanently locked within massive glacial ice sheets. Because the lighter isotope is trapped on land, the remaining seawater becomes highly concentrated with the heavier oxygen-18. Conversely, when the planet warms and the glaciers melt, the oxygen-16 rushes back into the sea, resetting the ratio. As marine organisms, particularly microscopic conodonts and reef-building brachiopods, extract calcium and carbonate from the water to build their shells, they unknowingly incorporate this exact isotopic ratio directly into their crystalline structures. When these organisms die and fall to the seafloor, they create a permanent geological ledger of the global climate. By vaporizing these ancient shells in modern mass spectrometers and measuring the exact ratio of oxygen-18 to oxygen-16, geochemists can calculate the precise temperature of the Silurian oceans and track the expansion or collapse of polar ice with staggering accuracy. However, we must acknowledge the strict limitations of this scientific model. We are attempting to read an atomic thermometer that has been buried under millions of tons of rock for over 400 million years. Over deep geological time, heat, pressure, and the percolation of groundwater can cause the calcium carbonate to recrystallize, a process known as diagenesis. This geological alteration can scramble the original isotopic signature, blurring the data and forcing scientists to constantly cross-reference multiple fossil sites across the globe to filter out the geological noise and find the true planetary signal. When geochemists successfully filtered the data from the late Silurian, specifically focusing on a geological boundary known as the Lau Event, they did not find a stable, warming ocean. They found a massive, chaotic disruption in the isotopic record. The data revealed a sudden, drastic fluctuation in global temperatures, coupled with a catastrophic collapse in the oceanic carbon cycle. This was not a localized extinction. It was a systemic failure of the planetary life support system. The mechanism driving this collapse was directly tied to the biological revolution occurring on the landmasses. As the newly evolved terrestrial roots broke apart the continental rock, they unleashed a massive influx of trapped nutrients, primarily phosphorus and nitrogen, washing them directly into the shallow epicontinental seas. This sudden chemical abundance overloaded the marine ecosystem. It triggered colossal, runaway blooms of microscopic algae that choked the surface of the water, blocking out the sunlight and disrupting the delicate food web of the ancient reefs. But the true devastation occurred when these algal blooms died. As billions of tons of dead organic matter sank toward the ocean floor, swarms of aerobic bacteria immediately began to consume the decaying tissue. To fuel this massive decomposition process, the bacteria stripped the surrounding seawater of its dissolved oxygen. This biological suffocation was compounded by the fundamental laws of physics. The isotopic record indicates that the global climate was experiencing intense warming pulses during this period. The physical reality of fluid dynamics dictates that warm water fundamentally holds less dissolved gas than cold water. The Silurian oceans were already operating at a reduced oxygen capacity due to the heat, and the bacterial decomposition completely exhausted whatever oxygen remained. The result was widespread oceanic anoxia. The water column was stripped of its life-giving gas, creating massive, suffocating dead zones that wiped out entire ecosystems of armored jawless fishes, sea scorpions, and the vast calcite reef structures that had defined the early Silurian. This leads to a far deeper, far more terrifying consequence. When oxygen completely vanishes from an oceanic environment, the biological hierarchy undergoes a lethal inversion. In the absence of oxygen, specialized anaerobic bacteria, which have existed in the deep shadows since the dawn of the planet, suddenly rise to dominance. These primitive organisms do not breathe oxygen. They respire using dissolved sulfates. The metabolic byproduct of this anaerobic respiration is hydrogen sulfide, an incredibly toxic, highly corrosive gas that is lethal to almost all complex animal life. During the Lau Event, the deep oceans literally turned poisonous. The water became saturated with hydrogen sulfide, likely tinting the seas a sickly pale purple. As this toxic, anoxic water upwelled from the deep ocean basins and spilled over the shallow continental shelves, it acted as a chemical scythe, cutting down the diversity of the epicontinental seas. At a planetary scale, the implications of oceanic anoxia change completely. When astrobiologists evaluate the long-term survivability of life on exoplanets, they recognize that an ocean is not inherently a permanent sanctuary. The chemical balance of a global ocean is highly precarious, constantly caught in a tug of war between biological production and biological decay. If an alien biosphere triggers a runaway nutrient cycle, perhaps through its own aggressive evolution, it can completely strip its oceans of oxygen and suffocate its own complex life forms. This mechanism serves as a profound great filter. A planet might successfully spawn multicellular life, only to periodically wipe the slate clean whenever the biogeochemical thermostat fails. For a world to eventually produce a spacefaring technological civilization, its biosphere must somehow survive these massive, suffocating pulses of anoxia. Life must be resilient enough to retreat into highly isolated, oxygenated refuges, holding onto its complex genetic code while the rest of the planet suffocates in a toxic soup. The survivors of the Lau Event were those few, rugged lineages that managed to endure this chemical apocalypse, carrying the hard-won biological innovations of the Silurian forward into the unknown. The Silurian period did not end with a single fiery apocalypse. Instead, it closed through a series of grueling, suffocating chemical bottlenecks. But as the toxic, anoxic oceans gradually stabilized and the global carbon cycle rebalanced, the biosphere that emerged on the other side had been fundamentally transformed. The Silurian was not merely a chapter of post-glacial recovery. It was the ultimate biological forge. In the span of roughly 24 million years, life on Earth transitioned from a passive, defensive existence into an active, high-energy paradigm. When we catalogue the evolutionary legacy of this period, we are essentially looking at the prerequisite hardware required to build a modern, technological world. By violently repurposing a cartilaginous respiratory arch into a hinged jaw, the early vertebrates unlocked the thermodynamic ceiling of the oceans. This single anatomical hack provided the concentrated caloric density necessary to eventually fund the enormous metabolic cost of a complex central nervous system. By engineering microscopic tracheal tubes and secreting waterproof lipid waxes, arthropods conquered the lethal vapor pressure deficit of the atmosphere, proving that an ocean-born organism could encapsulate its internal fluids and walk across a dry, irradiated rock. And by synthesizing chaotic chemical polymers like lignin, primitive plants defeated the gravitational pull of the planet, fracturing the bare continents and manufacturing the very first layers of organic topsoil. These are not isolated biological trivia. At a planetary scale, their meaning changes completely. These three innovations, high-efficiency energy capture, atmospheric gas exchange, and structural vascularity, are the mandatory mechanical bridges that any biosphere must cross to escape its evolutionary infancy. When we scan the galaxy for signs of intelligent life, we must realize that a chemically habitable exoplanet is simply a blank canvas. For a world to eventually host a species capable of manipulating fire, forging steel, and transmitting radio waves into the cosmos, its local biology must successfully navigate the exact same gauntlet of physical laws that defined the Silurian. It must learn to harvest concentrated energy. It must learn to seal its moisture against the vacuum of dry air. And it must invent biological concrete to build a lasting agricultural foundation. The organisms that survived the fluctuating oxygen levels of the late Silurian oceans and the harsh, shifting climates of the continents were no longer fragile pioneers. They were heavily tested, highly adaptable biological machines. As the calendar of deep time rolled forward into the dawn of the Devonian period, these survivors were perfectly positioned to exploit the newly engineered planetary environments. The microscopic vascular plants would soon explode into the first globe-spanning, deeply rooted terrestrial forests. The struggling jawed fishes would rapidly diversify to completely dominate the marine food web, ultimately setting the stage for the first vertebrate invasion of the land. The Silurian period proves that planetary evolution is not a gentle, continuous upward slope. It is a series of brutal physical and chemical barriers where life is repeatedly crushed against the strict laws of fluid dynamics, gravity, and thermodynamics. But it is precisely this unforgiving friction that forces the invention of complex architecture. Every breath of dry air we take, every complex thought processed by our calorie-hungry brains, and every mechanical advantage we hold over the physical universe can trace its foundational engineering back to the shallow, sunlit seas and the barren, rocky shores of the Silurian Earth. It was the crucial era where life stopped merely surviving the planet and finally began to conquer it.